Now the next theorem is this one. It states that H and K be normal subgroups of G such that H is a subset of K. Then the quotient group K by H is a normal subgroup of G by K. Here it's given that both H is a normal subgroup of G, K is a normal subgroup of G, H is a subset of K. Now if H is a subset of K, then it means that H is not only a subgroup of K, but it will be a normal subgroup of K. So that's why we can form the quotient group K by H. So K by H will contain these elements of the form Hy such that Y belongs to K, and G by H as H is normal in G, so we can form again the quotient group G by H is equal to set Hx such that X belongs to G. So now this what we need to prove is that K by H is a normal subgroup in G by H. So first of all, let us show that K by H is a subgroup of G by H. So let us just recall this theorem on subgroup. H is a subgroup of G if and only for every A and B belongs to G, AB inverse also belongs to H. So by using this theorem, we need to show that for any Hx, Hy belong to K by H. If I can show that Hx into Hy the whole inverse still belong to K by H, then I can conclude that K by H is a subgroup of G by H. So for this one, let us show down. So take Hx into Hy the whole inverse, but Hy the whole inverse is same as Hy inverse. We have discussed this one in the quotient group. So Hx into Hy the whole inverse is called to Hx Hy inverse, and this is called to H into Hx Y inverse. Why? Because H is a normal subgroup of G. It implies that Xh is same as Hx. So now also here we consider this one X is in K. So here as H is also a normal subgroup of K, H is a normal subgroup of K, so Xh is equal to Hx. So this is equal to Hxy inverse. And this will belong to, because X is an element of K, Y is an element of K, Y inverse also belong to K because K is a subgroup. So this implies that XY inverse also belong to K. So now this element XY inverse will be an element of K, and so this element H into this element will be of the form Hy such that Y belong to K. It is of the form HA such that A belongs to K. So this will imply that it will belong to K by H. So which means that this one Hx into Hy inverse belongs to K by H. This implies that K by H is a subgroup of G by H by this theorem. Now to show that K by H is normal in G by H, you take any element Hx in K by H where X belongs to K, and take another element Hg belongs to G by H where G is an element of G. Now show that Hg into Hx into Hg the whole inverse belongs to K by H, because if you remember the definition of normal subgroup, H is a normal subgroup of G if and only for every X belong to G, H belong to H. If Xh, X inverse still belong to H, then we can conclude that H is a normal subgroup of G. So here, what we have now is that instead of X it is Hg, and instead of H it is Hx. So Hg into Hx, Hg the whole inverse, this is equal to Hg, Hx, you can remove the bracket. Now Hg the whole inverse same as Hg inverse. So this is called to Hg. Okay, it is Hg, Hh, Xg inverse. So this is called to Hg, Hxg inverse. This is possible. Xh is same as Hx, as H is a normal subgroup of G. So and Hh is same as H only. So this is equal to Hh Gxg inverse. Again Gh is same as Hg, as H is normal in G. So again Hh is same as Hgxg inverse. Now this element here, X is an element of K, G is an element of G, and since K is a normal subgroup of G, this is given to only. So Gx, so this one Gxg inverse also belong to K. So this element belong to K. So if it belongs to K, so what are the elements of K by H? It is to form Hy such that Y belong to K. And since Gxg inverse belong to K, it implies that this element now is an element of K by H. So therefore, it implies that now K by H is a normal subgroup of G by H. So this proved the theorem. Now let me come to the next one, that is this. The set AG of all automorphism of a group G forms a group with respect to composite of function as composition. What is AG? AG contains all those 1, 1 on 2 homomorphism from G to G itself. So now let us show that it satisfies all the group axiom. That means AG, which contains only the isomorphism from G to G, satisfy the group axioms. So number 1 is this. For any the closure property, let us show this, prove this one. For any f and g belongs to A of G, I need to show that f composite G belong to AG. So now we know that f is 1, 1, g is 1, 1, as it belongs to A of G. It means that their composition also will be 1, 1. Similarly, f is on 2, g is on 2, so it means that f composite G is on 2. This is from the properties of mapping. But only thing left now here is that we need to show that f composite G is homomorphism. So how to prove that f composite G is a homomorphism? We can take these two elements. Suppose x and y belongs to G. Then what is G composite f of xy? It will be equal to, sorry, here I need to show that G composite f, okay. It will be, it's okay, I can show that f composite G also. F composite G of xy is equal to f of G of xy. And this is equal to f of gx G of y. Why this is possible? Because G belongs to AG, so G is a homomorphism. So gxy is same as gxgy. And again, f is a homomorphism. As it belongs to A of G, it will be same as f of gx into f of G of y, which is same thing as f composite G of x and f composite G of y. So this means that f composite G is a homomorphism. So therefore, this for any f and G belongs to A of G, f composite G is also 1, 1. F composite G also is a homomorphism. It is 1, 1 and on 2, so it means that it belongs to A of G. Now, associative law holds in AG. This is trivial only because we know that from the properties of mapping, that homomorphism of mapping always satisfy a composition of mapping always satisfy the associative property. That is, for any f gh belongs to A of G, f composite G composite H is same as f of G composite H. So we need not show that one. Now, existence of identity element in AG. As we know that the identity mapping is always an element of AG. Why? Because identity mapping is always 1, 1 on 2. And also, I of xy, for xy belong to AG, it is equal to xy, which is same as ix into I of y. So it means that I is a homomorphism. So this identity mapping for any f belong to AG, f composite I of x is equal to f of ix. But what is ix? It is x itself, so it will be x. So you can see from here that f composite I of x is equal to fx, which means that identity mapping from G to G will act as the identity element in AG. And the last one is this one, existence of inverse element. For any f belong to AG, since it belongs to AG, it means that f is 1, 1, f is also on 2. So that means f inverse will exist. This again from the properties of mapping. If a mapping f is 1, 1 and on 2, then its inverse also will exist, and at the same time the inverse also will be 1, 1 and on 2. Now the only thing left here is to conclude that f inverse belong to AG. I need to show that f inverse is a homomorphism. So how to prove that f inverse is a homomorphism? You take this one, let x belong to G. Okay, let us take x and y belong to A of G, such that f inverse of x is equal to x prime, f inverse of y is equal to y prime, where x prime, y prime are again element of G. Now, From here, it will implies that x is equal to f of x prime, and from the second one, y is equal to f of y prime. Now let us show what is xy. fxy is equal to fx prime into f of y prime. But as f is homomorphism, this is given only. F is homomorphism as it belongs to A of G. So therefore, this will be same as fx prime y prime. So it means that xy is equal to f of x prime or x prime into y prime. So this implies that this one f again belongs to f of g. So xy is equal to f of x prime y prime will implies that x prime y prime is equal to f of xy inverse. That means you can as f inverse x's. Okay, so you can multiply by f inverse on both sides. So therefore you get f inverse. This will become f inverse. Here it will be f inverse of xy. This is equal to x prime y prime. But what is x prime? It is f inverse of x. And what is y prime? It is f inverse of y. So which means that f inverse of xy is same as f inverse of x into f inverse of y. This shows that f inverse is a homomorphism. So this proof that every elements of AG, that means every mapping F defined in belongs to AG has an inverse in itself. Therefore, this set AG which contains the mapping F defined from G to G which are isomorphism, that is 1-1 onto homomorphism, satisfy all the group axioms. Now hope it is clear regarding this term. You just go through it. In case if it is not clear, you please let me know.